Hi guys! Today's video is a little bit different. We're going to be asking you to be annotating and coloring your own periodic table. So before you get started, we need you to go ahead and make sure you do have your hard copy of your periodic table and some pencils or crayons to color things in, or highlighters.
So today we're going to be starting to talk about ions before we look at the arrangement of the table. And ions we've already mentioned with nuclear chemistry, but hopefully you've gathered already that they are atoms, and we'll see groups of atoms also that have a positive or a negative charge because they've gained or lost electrons. They're going to gain or lose electrons so that they can have a noble gas configuration. Now for most atoms that means that they're going to have 8 total valence electrons. That's what their goal is, because most of the noble gases have 8 valence electrons. We do see some exceptions where they will gain or lose electrons to look like helium, which only has 2 valence electrons because it only has one s shell.
Okay, and the reason why we've been talking about valence electrons is because it directly relates to what type of ion and the charge of the ion that an atom will have. So the number of valence electrons helps us to determine an ion's charge. I'm going to use magnesium as an example of that in a moment. But first I'm going to talk about cations, and cations are positively charged ions. I tell everyone you can remember that because a cat has paws, and so it's positively charged. This is my, cat. Okay. And cations are positively charged because they lose electrons. So their net charge means that they have more protons than they do electrons. So that's why they're positively charged. My example is magnesium.
Right here.
And you can see, because it's positioned on the periodic table, magnesium has 2 valence electrons. Now, if it wants a full valence shell, or it wants to complete this Lewis dot structure, the easiest way to do that is to just get rid of these 2. Give these 2 electrons away. So in this example, that means we are just going to get rid of these outer 2 electrons, and that whole last energy level disappears. And then you can see that we have 8 right here. And so magnesium is happy. And it will have a 2+ charge. I lost 2 electrons. Because it lost those 2 electrons, and we're going to write its Lewis structure diagram like this. 2+, I don't remember. Anyway, okay. So based on its electron configuration, this is what we would have: 1s2, 2s2, 2p6, 3s2. It is going to, these are my valence electrons right here. It's going to get rid of those 2 or give them up. And so +2 charge for magnesium is going to actually be 1s2, 2s2, 2p6, 3s, nothing. So we just get rid of that. And we have a total of 8 valence electrons. Yay.
And we see there that we lost an energy level. So the cation there is actually smaller than that parent atom that it came from. So the magnesium ion is going to be smaller than
A magnesium
atom. We see the opposite with anions. Anions, which I'm going to talk about in a sec, are bigger than their parent atom. All right, so they're going to be a little bit larger than their parent atom. An anion is a negatively charged ion. You can remember that because, well, this is how I tell my students, a negative ion. Anion, a negative ion. It's negative because it's gained electrons. Remember that electrons have a negative charge. So if an atom is gaining negative charges, it will become negatively charged. I'm going to show you an example with fluorine. Fluorine is in our halogens group, which Ms. Thompson is going to show you. It's in our halogens group, so it has 7 valence electrons. We can see that here in the Bohr model. We can also see it here in our Lewis structure. Now, fluorine, opposite of magnesium, it's going to be a lot easier for fluorine to actually gain to have a full outer shell of 8 valence electrons versus losing 7. 7 is a lot of electrons to lose, so it's going to gain 1 electron. Or in our Lewis structure, we would see that 1 electron gained here. When we draw the Lewis structure for the fluoride ion, we actually see, right, there's our 2 in the S, 1p, 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 another p, another p, another p. We have a full valence of electrons right there, and fluoride has a negative charge. So that's the Lewis structure for the fluoride ion. Fluorine, its electron configuration we see is 1s2, 2s2, 2p5, right? Ooh, 2s2, 2p5. The fluoride ion is going to gain that one electron, so instead of 2p5, we have 2p6. Now here are the valence electrons, 2 plus 6, they're both in the second energy level. We have 8 valence electrons total. Now what you want to notice is that magnesium ion and fluoride ion now have the same exact electron configuration, 1s2, 2s2, 2p6. They have the same configuration of neon, which is a noble gas, all right? And that's fine. They can have that same configuration. Now we're going to move to talking about...
So they both look now like neon. Their electron cloud is going to be the same as neons.
We're going to look now at the periodic table arrangement. There we go. The periodic table, we've talked about how it's pretty amazingly arranged, right? It's very methodical on how this was all put together. It's arranged in order of increasing atomic number. So if you look from hydrogen and on, we have 1, 2, 3, 4, 5, 6, 7, 8. Increase in atomic number from left to right across the periodic table. We talk about the table in terms of rows and columns. The rows, which are horizontal, were referred to as periods. The columns, which are vertical, we refer to as groups or families. Now, the periodic table is also arranged in terms of metals, nonmetals, and metalloids. Generally, everything left of this big, bold stair-step line, we know are metals. Everything to the right of that line, nonmetals, and everything that lies on that line, we call metalloids. I'm going to start with metals. So again, everything left of the stair-step line. Metals are good conductors of electricity, and you should know that based on appliances in your house, technology. We use copper wires, things like that. They're good conductors of electricity. They're solids at room temperature for the most part. One exception, or the exception, is mercury. So if you're looking on the periodic table, killing me here. Hg right there, mercury, is a liquid at room temperature. If you've ever seen a mercury thermometer, the reason that works is because mercury is liquid. Other properties of metals is that they're shiny, they're malleable, and they're ductile. So they could be shaped into wires or flat metal.
And nonmetals are found to the right of the staircase or stair-step line. They are not good conductors of heat or electricity, and they are mostly gases except for our exceptions, which are bromine, liquid at room temperature, carbon, phosphorus, sulfur, selenium, and iodine are all solids at room temperature. Other properties include that they are dull, and which means they are not shiny. And like Ms. Frankovic already mentioned, metalloids, they're found along right on that stair-step line. We're going to show you specifically which ones those are in just a second. But they have properties of both metals and nonmetals, and we'll investigate some of those throughout the year.